Hey everybody, Walt here for OverKill Projects. Today we're going to take a look at some op-amp basics and also some advice for how to take your skills to the next level, start yourself on the path to become a true graybeard. Let's get started. I thought I'd start out today with a little bit of advice that helped me an awful lot. So if you want to hear that, stick around. If not, and you just want to see some circuit analysis and that sort of stuff, then whatever time I put down here, skip ahead to that. You can check that stuff out. But if you're new to this, or even if you're not new, if you've been around a while, but you're looking to sort of take your game to the next level, then maybe you want to hear what I have to say. So in case you're new here, which you are because I'm new here, this vlog is all about electronics and product design, sort of makerspace stuff, and how to sort of accomplish what you're looking to do with your ideas. And now when you first get into electronics and design, whether it's a hobby or you're a student or you have some sort of product idea or something like that, one of the biggest issues is that you're not good at it. And there's not a lot of ways to get good at it other than to sit down and just sort of truck through a book or something like that. But even if you spend your time learning the basics of, all the passive components and stuff like that, and even some of the basics about op amps, and we're going to go over some of that later, you still need a way to practice. Electronics is just like any other field. It's a lot like learning the piano or something like that, something else I've gone through kind of recently, but you need to have something where you can push yourself a little bit further and practice with it. Learn a little bit more and a little bit deeper and a little bit wider. That's how you're going to really get better. And now practicing more and better, because it's not just about practice, it's also about practicing correctly.
We're talking about practice, man.
You're going to find that you're going to get to a point where when you have an idea for something, you want a circuit that will do something, you'll sort of just get a feel for where to start, how to begin building up that circuit, because you've done it so many times that it just becomes second nature. But now once you exhaust sort of like the basic textbook electronics, where do you go? How do you find another circuit to practice on? Well, an obvious source, of course, is just, your own ideas. You can sort of fiddle around and come up with things, and there's really nothing wrong with that. You can always sort of pick a couple parts of DigiKey or wherever you get your parts from and just screw around until something kind of works for you. But something that I find works an awful lot better is to use the advice of people who are already fantastically brilliant. And the way that you get their knowledge is to take a look at the things that they think are important. And it turns out that some of the most brilliant people in the electronics and design industry have been giving you the resources you need all along. And those things are app notes. App notes are brilliant. There are app notes from every manufacturer about every part that you could possibly imagine, and some of them are just ridiculously good. Not only are they good in the information that they give you about how parts work and fit together and how to build circuits and stuff like this, but they are literally just like a gold mine, a treasure trove of circuits that you can practice. So today we will start going through my favorite app note, AN31, the op-amp collection application note written by the late great Bob Pease. If you don't know who he was, check it out down below. Absolute titan in the industry, really cool guy. This app note's been around for a longish time. It was originally National Semiconductors, now it's updated by Texas Instruments. It's a great app note if you're just getting started out with op-amps. There's no end of circuits to try out in here. There's 70 different circuits listed. There's a million variations. You can do, single supply, dual supply. You can vary all the components, all that sort of stuff. Gives you amazing insight into just how these things work and how to design circuits around them. So without further ado, let's open this bad boy up and start taking a look. When we say op amp or operational amplifier, we mean two different things. We either mean op amp, probably can't see that, or we mean op amp. When I talk about this op amp, I'm going to call it a real op amp. When I talk about this op amp, I'll be calling it an ideal op amp. Ideal op amps, the symbol are just that. They're a symbol. They're not meaningful in the real world. They're just a tool that helps us analyze circuits. Looking at our ideal op amp symbol, we see that there are 5 pins. We have two inputs. There's an inverting and a non-inverting input, and we'll get to that in a minute. There are power supply rails, so there's a positive voltage and a negative or ground voltage. We can think of it as just the high level and low level power supply voltages. And then there's an output pin. In general, when we're looking at the ideal op amp, we're not so concerned about the power supply, at least not at first. So you'll often see the symbol drawn without the power supply pins, which really makes an op amp a 3-terminal device. When we talk about ideal op amps, they're going to follow 3 rules that do not apply to real op amps in the real world at all. Our first rule is going to be an open loop criterion. So if we have our op amp in an open loop circuit, we're going to assume that the gain is infinite. Rule number 2 is that an op amp in a closed loop circuit does everything in its power to try to make the voltages at both of its inputs the same. That's the same as saying that it tries to make the difference between the inverting and non-inverting inputs 0. And finally, our third rule for ideal op amps is that there is no input current at either of the input pins, which is the same as saying that an op amp has infinite input impedance. Now going back to our rule number 1, even though we're not going to use op amps in open loop configurations very often, it's important to know that the way the op amp is going to work is it's going to look at the voltages at both of the input pins, and whichever one wins, it's going to immediately output that supply line. So if the non-inverting input voltage, usually given by the plus, is the higher of the 2 voltages, then the op amp is going to output a voltage equal to the high supply line voltage. On the other hand, if the inverting input pin, given by the minus, is the greater of the 2 voltages, then it's going to output the lesser voltage supply pin voltage. Yeah. And in the case that they're equal, the op amp should output 0 volts. Now in theory, in an ideal op amp, this should happen with infinite speed. It should immediately jump to either the high, low, or 0 voltages. However, in practice, this is not how it works. Actual op amps have something called a slew rate, and that gives a fastest speed at which the op amp can change its output voltage. For some op amps, this is very low, in fact, and for others, it can be extremely high. Typically, op amps with extraordinarily high slew rates are called comparators. It should be immediately obvious why they're given this name, since really what these op amps do is compare the voltage at the 2 input pins and then output a signal that gives you a representation of which pin won. So far, hopefully this all is coming together just fine, because now when we move to closed loop configurations, the picture gets a little more difficult. We actually have to do some analysis. The simplest closed loop configuration we can have for our op amp is something that's actually called the unity gain amplifier. In the unity gain configuration, we tie the output voltage directly back into the inverting input of the op amp. And then our incoming voltage, which could be like a sine wave or just a DC voltage, comes into our non-inverting input pin. So rule number 2 told us that in a closed loop, the op amp is going to do everything it can in order to make the voltages at the 2 input pins the same. We have an input voltage at the non-inverting pin, just call that V in. So in order for the op amp to make the input voltage at the inverting input the same as V in, it has to output a voltage equal to V in. And so we get that voltage out is the same as voltage in. Unity gain, a gain of 1. Now, if you're just starting out, this might not seem very useful at all. It might actually sound a little ridiculous to have the voltage out be the same as the voltage in. Who would even need that, right? But it might surprise you to know that this is a very common use for op amps. We use this configuration because the output impedance of an op amp is very, very low. So if we are getting an input voltage from a source that has a relatively high impedance and it won't be able to supply much current to our circuit, then if we buffer it through a unity gain amplifier, we're going to have much more current available at that voltage. We can put that extra current towards driving something bigger. So we could drive a motor, or we could drive a speaker, or something that requires a large amount of power that otherwise wouldn't be able to be powered from our high impedance input signal. Pretty useful. So now let's take the closed loop configuration one step further and check out the first couple of circuits from AN31. The first circuit here you can see is a very close cousin of the unity gain amplifier. It's called the inverting amplifier. In fact, it looks just like the unity gain amplifier, except for now you can see that we have resistors both on the input itself and on the feedback loop between the output and the inverting terminal. And handy enough, the app note gives us the formula for gain just below the circuit diagram. It's negative R2 divided by R1. But it's not fun to just take the app note's word for it. If this is going to be a learning exercise, we should go ahead and see if we can't derive that ourselves. And we can, it's not that difficult. I'll show you how. First, let's agree to call the current that comes out of resistor 1, I1, and the current that comes out of resistor 2, I2. Now we know by rule number 3 for ideal op amps that no current actually goes into the inverting input of our op amp. So now if we employ Kirchhoff's law for currents, we know that I2 plus I1 must equal 0. We can rewrite that as I1 equals negative I2, and now we know that I1 is the same as V in times R1, and we know that I2 is the same as V out times R2. So if we substitute those and rearrange a little, boom, magic. We get the formula that we see in the app note. But now, like we were saying earlier, this is for ideal op amps. In the real world, a real op amp is going to perform far differently. There's going to be all sorts of different types of error that occur that are going to change the way this circuit works depending on our input voltage. Let's take a look at 2 of these and see how they interact with the formula that we just derived. First, let's consider something called the input voltage offset. So before we said that the op amp will output a 0 voltage if the input voltages are identical. But this was wrong. It turns out that in the real world, a real op amp requires a slight difference between the two input voltages in order to output 0 volts. In real op amps, this offset voltage can vary considerably. It can be over 10 millivolts, it can be down into the nanovolts, and it can have a real impact on the way that your output signal looks. Another real spec that often has real impact is the input current error sources. There's actually more than one source for this type of error, but the 2 biggest offenders tend to be input bias current and input offset current. So now let's assume that neither of those are 0 for this op amp configuration for a given op amp, and see if when we derive the equations, if there's any significant difference. First, let's call the sources of real input current delta. Then when we got to the point in our derivation that we arrived at Kirchhoff's laws, we had set them equal to 0. We had I1 plus I2 equals 0. But now we would have I1 plus I2 equals delta. If we agree to call our input voltage offset epsilon, then our current across R1 is going to be given by V in minus epsilon divided by R1. And likewise for I2. So now if we plug in everything that we know and we rearrange and try to rewrite this as voltage out again, we see that we arrive at a slightly different formula. But it doesn't look so different from what we had before. There just happen to be 2 extra terms. And now you can see that if both delta and epsilon were 0, we would actually arrive at the formula that we originally derived. If we were building this out as a precision circuit, we would have to do an analysis of this sort in order to allow for the types of error that we might see in the op amp that we're using. Or we might actually want to derive an equation like this first in order to make sure that we choose the right op amp to minimize the impact of those 2 parts of this formula. And as it turns out, something that you pretty much have to get used to right away when you start building out circuits of this sort is that in a real op amp, there's going to be a lot of trade-offs. If you want to minimize input offset voltage, you're going to have to sacrifice something else somewhere else. Hopefully you get the idea and you see that it's not that difficult to derive these formulas. They're not particularly scary, but they are extremely useful when you're doing analysis for real circuits, especially if you're doing some sort of precision work. And in fact, if we were really worried about precision here, we would be opening up the data sheets for our op amps, putting in the maximum and minimum figures for those. If we were using 1% resistors, we would be putting in maximum and minimum values for those as well in order to see just what range of output gain we can expect. There is one thing that you should note from this circuit though before we move on to the non-inverting amplifier, and that is the protection resistor, R that they have running from the non-inverting input to ground. The app note says that this is to protect the op amp from current spikes, and this can be a thing, especially during power up and power down. As supply voltages vary, you could have a scenario where the ground voltage all of a sudden spikes up or down and causes a large increase in input current at those terminals. That large current can damage the device, can actually blow it up, and so putting a 10K resistor in series with ground means that you're not gonna have to worry so much about that. You divide your input voltage by 10,000 and you get probably a very small current. And you'll also note that, for example, in this app note, there's a reference to another application note that gives you more information on how to choose that resistor value. So between referencing that and building this circuit a couple times, it should give you enough experience to understand just exactly what effect these different components have on the finished circuit. And now if we take everything that we just said about the inverting amplifier and take a look at the non-inverting amplifier, we'll see that it analyzes almost the exact same way. If we take the non-inverting amplifier given in app note 31, we can redraw it just a little bit so that it looks like this. And drawing it this way, we see that it's actually more straightforward to analyze than the inverting amplifier was. In this case, we have the inverting input hooked up to a voltage divider. Then we apply an input voltage at the non-inverting pin. We know by ideal op amp rule number 2 that the voltages at both of the input pins have to be the same. So we have V in on both the inverting and non-inverting terminals. Now it's just a matter of applying the voltage divider equation. We have that V in, at least the V in that's on the inverting input, must be equal to V out times R1 divided by R1 plus R2. Now rearranging, we see that V out has to be equal to 1 plus R2 over R1, that quantity times V in. And so our gain figure is 1 plus R2 over R1. Something you should notice right away is that this means that for a non-inverting amplifier, it's impossible to have our gain be less than 1. So this topology is only useful if we want our gain to be bigger than unity, which is pretty much the same as saying that the non-inverting amplifier makes a bad unity gain follower. I'm gonna go turn on the soldering iron and get to work putting the circuit together for you so we can actually look at it on the oscilloscope. Let's go. All right, so that was super simple. Not a lot going on in this circuit. I put a little dot next to the 1 pin on this op amp, and I do that with nearly all of the ICs that I use. I just take a little acrylic marker pen, little fluorescent guy here, and just put the little dot next to pin 1. It makes it really easy for me when I go to reuse this to see exactly where pin 1 was. I can just slap it into a circuit in no time. Sometimes I even write what the IC is on the surface, but there's no room on an 8-pin package. And besides that, this has pretty readable text on it, so I don't really need that, but just something to keep in mind. Oh, and I guess I never really said, but I put this on a piece of strip board. Strip board is just, you can see it's clad with rows of copper on one side. And now those act as sort of like bus bars that run all the length of the board. Now in a case that you put a dual inline package like this onto a board like this, you're going to actually need to take a razor blade or a knife and cut those bars straight across where the IC is. That way, in this case, say, pin 1 is no longer connected to pin 8, pin 2 is no longer connected to pin 7, and so on. You need those to be separate. And one thing that you should do when you make those cuts is fire up your multimeter and just make sure that the resistance across that gap is infinite. And that's before you put the IC in. If you do it after you put in your op amp, you're not going to get this consistent value, right? So when the op amp is off and you go to measure the resistance across that gap, you're actually going to be measuring it also across the internal components in the op amp, and so you can't trust that figure. Whatever, just make sure you do it before you actually have things on the board. And I opted for a strip board over a breadboard because breadboards have a lot of stray and parasitic impedance. If you don't know what that is, I'm really just saying that if you build on a breadboard, you're going to add in inductance, capacitance, and resistance that you didn't have in your ideal circuit diagram. Now, we're also going to run into those problems on strip board, but there's going to be a lot less of that stuff than there would be on a breadboard. Of course, now that I say that, I wonder just how much less. I should probably test that at some point, and you should too. But for now, I'm not going to worry about it, and we'll just go ahead and take a look at this circuit as it is. And here you can see a close-up of our circuit on the strip board. In the socket there, we have the classic and venerable TL071, and its pinout is actually based on the even older sort of OG op amp, the 741. If you don't know about the 741, you should look it up. It's pretty classic piece of electronics history. And speaking of the pinout, here that is. You can see pins 2 and 3 are our inverting and non-inverting inputs. Our output is on pin 6. Our supply lines are on pin 7 and 4. We have a no connection pin on pin 8. And then you'll see 2 offset pins. Those are included so that you can add in a little bit of extra hardware, some resistors and a potentiometer in order to null out the input offset voltage of the op amp. However, we're gonna go ahead and leave those open in this case, since we're not so worried about getting into the nitty gritty of how those sort of things work. But in future circuits, we'll probably make use of those pins in order to reduce the amount of offset that we see and improve the performance of our circuits. And you can see here that the circuit actually follows our original circuit diagram pretty closely. We have all the resistors that were present on the original here. The only difference is that I have R2 in this circuit is a 100K resistor. And I did that in order to give us a gain of -10, which I thought would be a little bit more interesting when we look at it on the scope than just doing a unity inverting amplifier. I also made the change for the compensating resistor R on the non-inverting input. I went with 9.2K ohms of resistance for that instead of the 10K ohms that you see in the datasheet. I did that to turn this resistor into a true compensation resistor. I don't think that it'll make any massive performance difference, but I had them sort of sitting on my desk, so I figured why not. And I didn't really cover the idea of that resistor being a compensation resistor when I first talked about it, but you'll notice that the value I went for that resistor here is actually R1 parallel R2. And that's not a coincidence. And in fact, this has to do with trying to null out any input bias current that we see in the op amp. I actually decided not to discuss this earlier because I thought it kind of goes beyond the scope of what I'm doing here, but it's likely that I'll cover that later on during another tutorial. And if you're interested in deriving it yourself, just assume that there's an input bias current and calculate what the voltage drops would be on our resistors R1 and R2. Then, assuming that same bias current at the non-inverting input, figure out what value resistor you should put there in order to equalize that voltage drop so that the op amp doesn't have to output a different voltage in order to make up for the input bias current. And if you get R1 parallel R2 as your result, then you did it right. You can also see that my input voltage is going to come up at the top there before we go into that series resistor that goes into the inverting input. When we switch over to the non-inverting amplifier, I'm simply going to put the input voltage, which is going to come from a function generator, down on the non-inverting pin in series with the compensation resistor, and I'll move our ground point up to the inverting pin, obviously in series with R1, just like it's drawn in the diagram. Okay, so that does it for a review of the actual circuit. Let's take a look at how it performs on the oscilloscope. And this is our setup. You can see that I have a function generator up here that's going to output our voltage for us. This is going to be our V in. Here's our supply voltage. It's going to be supplied by our power supply down here. And over here, of course, is our oscilloscope. Okay, so here we have everything set up and running. And as you can see, we get exactly what we expected to get. So our input here is a 1 kilohertz 1 volt peak to peak sine wave. And we can see that represented here by the blue waveform. So channel 3 is going to give us our blue waveform and channel 1 is going to be our yellow waveform. And you can see that channel 3, the scope is displaying 500 millivolts per division. So we can see it's a 1 volt peak to peak sine wave. It goes 500 millivolts above 0 and 500 millivolts below 0. Likewise, we have 5 volts per division on channel 1, which is the yellow channel. So you can see here that this is the output, V out, is 10 volts peak to peak. So we're getting 5 volts above 0 and 5 volts below 0 here. And that's exactly what we expected to see. And of course, they are exactly 180 degrees out of phase because this is an inverting op amp. And actually, it's working like jarringly well here. Here, this display might give you a little better idea of what's going on here. So we have the exact same scale for both channels 1 and 3. Remember, 1 is the output and 3 is our input voltage channel. You can see that our yellow waveform is exactly 10 times our blue waveform, but negative. So we have negative 10 times gain here, just like you expected to see. And here we are with an input voltage of 100 millivolts peak to peak, same sine wave, 1 kilohertz. You can actually see that the scope picks up the frequency up here in the corner. I had to turn my noise reject on because without that, you can see that the waveform will start jumping around a little bit. And we end up getting that jitter just because the noise on the channel will cross 0 and the trigger picks that up and then adjusts the waveform accordingly so that it's in the center of the screen. And we get that noise because we have our probes, both of them actually have a ground probe loop in between them, and that loop creates a certain amount of inductance. That inductance then translates into this noise that you see sort of fuzzing up the edges here. It's hard to actually see. We can increase on the scope. You can see here now a fuzzier edge, but again, the scope is smart enough to have a noise reject function that keeps it from jittering around when that noise crosses the 0 mark. And now, just for sort of an intellectual exercise, here's what the scope output looks like when we take it down to an input voltage of 10 millivolts peak to peak. You can see that we actually have the same result. We have negative 10 times the input voltage from the blue waveform on the yellow waveform here. However, we see a ton more noise on these edges here. And that is not the amplifier. The amplifier is not really causing this noise, or at least it's causing almost none of this noise. Almost all of it is caused by improper probing techniques here. I effectively have all these inductance loops just sitting around the board, sitting around my desk, the surface. It's picking up all sorts of external noise. But you can see here the utility of this circuit. 10 millivolts peak to peak is a relatively small input, and in fact we could push this down even a little bit further, especially if we tried to remove some of the input voltage offset on this op amp, and we still will be amplifying our incoming signal by 10. And here we are back to our 1 volt peak to peak input. I'm actually going to go ahead and increase the frequency here, and we'll see how this op amp responds as the frequency increases. Here you can see that even though I've changed nothing on the oscilloscope, our output voltage is only now 4 volts peak to peak, 2 volts above, 2 volts below. Not only that, but something else you should notice is that we no longer have 180 degrees phase shift. Instead, it looks like we're almost at exactly 90 degrees phase shift. So where before we had, every time there was a low peak in the blue waveform, we had a high peak in the yellow waveform. Now we see that those two have this offset. So the op amp not only cannot amplify a signal at this frequency efficiently anymore, but it also adds some delay to the waveform itself. Here we are at 1 megahertz, and you can see pretty well that our output has shifted now even further. It's more than 90 degrees out of phase. It's actually now it looks like it might even be approaching the 180 mark, so maybe like 120, 130 degrees out of phase here. And also, it's not even 1 volt peak to peak anymore. So in fact, if we normalize the scale here by reducing them to the same scale, we see that we're barely getting any amplification here at all. Just a few millivolts, only about 200 millivolts peak to peak amplification at 1 megahertz. And now here I've swapped out the TL071 for another classic op amp, the OP07. The OP07 is another one of those classic op amps that has a 741-like pinout, so all I had to do was swap this one out. The offset pins are actually different between the two op amps, but since we're not using those, that's not going to be a problem here. And now this is going to give us an opportunity to see the difference between two different types of op amps. So our first op amp, the TL071, was a JFET input op amp, and so we saw pretty high slew rates. We saw that it didn't start to attenuate, and the phase shift stayed true to form up into what was it, a couple hundred kilohertz. But now you would pay for that with the TL071's relatively high input offset voltage, which can be as high as 10 millivolts. On the other hand, the OP07 here actually has a much lower input offset voltage. It maxes out at 250 microvolts, but its typical performance is well below that, which means that this op amp has something like 2 orders of magnitude better input offset voltage than the TL071. However, the OP07 is a BJT input amplifier, and so what we expect here is that we're going to pay for that lower input offset voltage with a much lower slew rate at the same supply current. And in fact, that's pretty much exactly what we see. These two op amps have nearly identical input currents, somewhere in the 1 to 2 milliamps range. And the TL071 has a slew rate of about 13 volts per microsecond, where the OP07 has a slew rate of only about 300 millivolts per microsecond. And so where we had about 2 orders of magnitude better input offset voltage, we actually have about 2 orders of magnitude worse slew rate. Now let's see what that actually means in terms of performance here. We see that at 1 kilohertz, we actually have almost identical performance to what we saw with the TL071. However, if I increase our input frequency to 13 kilohertz, where the TL071 was performing flawlessly in the audio range, we see that the OP07 already has a huge amount of distortion and a pretty good amount of attenuation on the output. In fact, at this frequency, the output looks a lot more like a triangle wave or a sawtooth wave than it does a sine wave. And now lowering the frequency just a little bit to see where we really start to run into problems, you can see that even at 7 and 8 kilohertz, we still have a little bit of distortion in the output sine wave here, and just a little bit of phase offset here. And it's not until we back it up to about 5 kilohertz that it really looks like we're getting a pretty high fidelity output, that we're seeing sort of exactly what we would hope to see by a 10 times inverting gain amplifier. And now there are dozens of other things we could check with the OP07 here and look for differences between it and the TL071. But this really isn't a video about categorizing op amps. This is sort of just meant to be an introduction to the inverting and non-inverting amplifier topologies. So I think that I'm going to cut it there. And here's our same setup in the non-inverting amplifier topology. You can see here that we were running a 5 kilohertz sine wave. It's sort of the same thing that we had before, 1 volt peak to peak input, and we're seeing 10 volts peak to peak output. And you can see here that the output is almost identical to what we would expect. There's maybe just the smallest amount of phase shift present that you can see sort of at the peaks, at the maximum and minimum of our output there. But it's really very minimal. And of course, that's going to go up as we increase our frequency. It will go down as we decrease our frequency. We could do the same checks that we did for the inverting amplifier to take a look at some of the performance things and even switch it out again for the OP07, but I'm gonna not bother doing that here. You see how the circuit performs and that it performs the exact function that we hoped it would. All right, how fun was that? That was amazing. It worked exactly the way we thought it should, up to the limitations of the op amps, and should hopefully give you an idea of just how useful these little black box type components can be in arranging your own circuits. Hopefully you found this both entertaining and educational, and if not, then hopefully one of the two. And if you did, make sure you give me a thumbs up down below, and make sure to hit the subscribe button. We'll be going through more of these circuits, of course, but we have a lot of other things planned. Hit the bell for the alerts. Make sure you comment down below if there's anything else you want to see from me. Oh, and check the description for links to various stuff that we dealt with today. It's great hanging out with you today, and I'll see you next time.
I know it's important. I do. I honestly do. But we talking about practice, man. What are we talking about? Practice? We're talking about practice, man.